Hello and welcome to Chapter 10, where we will discuss re-expressing data. We cannot use a linear model unless the relationship between the two variables is linear. We've seen this over and over again. Often, using re-expression can save the day. It can help us straighten bent relationships so that we can fit and use a simple linear model. When we re-express data, we will use a variety of mathematical functions to change our data values. We saw this yesterday with the goldfish activity when we square rooted all of our areas and it took that curved scatter plot and made it into a linear scatter plot. So our first example here looks at the relationship between fuel efficiency in miles per gallon and weight in pounds for late model cars. It might look fairly linear at first. You can kind of see a curve, but you might argue that it's somewhat linear. But when you look at the residual plot, there's a definite curved pattern here, which is telling us that a linear model is definitely not appropriate. So what we could do is re-express fuel efficiency as gallons per 100 miles, which is a reciprocal function, and then my scatter plot turns into this right here, which is much straighter. Again, if you look at the residual plot, it's still somewhat curved, but it definitely looks more reasonable than the scatter plot of the residuals that we saw up here. There are four main goals of re-expression. The first goal is to make the distribution of a variable more symmetric. So you may start off with a histogram that's very skewed, something that looks something like this here. But then as we re-express our data, we could turn it into something that looks more like a normal model, something that is more symmetric. The second goal is to make the spread of several groups more alike. So even if their centers are different, if I can take these differing groups and make them more alike, it's easier to make comparisons. The third group is to make the form of a scatter plot more nearly linear. This is probably the most popular goal that we'll see and use. It's the same goal that we used with the goldfish yesterday. And the fourth goal is to make the scatter in a scatter plot spread out evenly. So oftentimes we'll see scatter plots where I have clusters or groups, or things start off very clustered together and then become spread out. Re-expression can help us make this spread more even. So in our example here, we're looking at emperor penguins. They have the ability to slow their heart rates while diving. Here are three displays of their diving heart rates. We have box plots, a histogram, and a scatter plot. And we want to talk about what features of the graphs display that re-expression might be helpful. So in this first scatter plot, I'm seeing a pretty curved pattern here. So I would argue that I should use goal 3 here. I want to make the scatter plot more linear. The next one, I have a histogram, and it does look pretty skewed. So this would be an example of goal 1, where I'm trying to make my graph more symmetric. And the third example here, I have all these different box and whisker plots. They look kind of all over the place. I have some that have a very large IQR, some that have small IQR with no whiskers. I've got some over here with lots of outliers. There's no outliers. So this would be a great example of goal 2, making groups look more alike. Yesterday in class, we reviewed several different types of functions, including square roots, squares, and reciprocal functions. Today, we will review log functions, your favorite. So I'll go through a couple examples with you. In this first one, we're solving for y when x equals 2, and this is the equation that I'm working with. Just like we saw yesterday, I'm going to start with taking the x equals 2 and plugging it in. So I have y equals 2.5 plus 0.6 times log of 2. There's nothing really to solve here, no manipulating is necessary. I can just plug this entire function right here into my calculator and it should give me my answer. So I have 2.5 plus 0.6 log of 2, and I have 2.68. That is definitely one of the easier functions that we'll be working with. All right, example 2, same idea. I'm solving for y when x is equal to 2, but in this case now I have the log of y instead of logging x. I'll start again with substituting 2 in for x. So I have log of y equals 2.5 plus 0.6 times 2. And I'm going to start simplifying this side over here using my calculator. So I have 2.5 plus 0.6 times 2, which gives me 3.7. Now from here I have to remember back to Algebra 2, where we learned how to convert logs into exponentials. Every single log always has a base. If no base is given to you, then it's always a nice little invisible base of 10. When I go to rewrite this, I'm rewriting it into exponential form. My base will stay the same, so it's a 10. And whatever I'm taking the log of, and the other side switch spots. So the 3.7 becomes my exponent, and now this thing here is equal to y. Now I have isolated my variable, so I can use my calculator to type in 10 to the 3.7th power, and I find out that y is equal to 5,011.87. The big idea to remember with logs is your basic rule that if I have log base b of x equals y, to change that into exponential form, your base of b stays the same and x and y switch spots. Go ahead and pause the video. I want you guys to try example 3 on your own. Once you're done, you can unpause to check your answer. All right, hopefully you got 3.16 for your y value. I've included all my work here so you can check your answers. In example 4, we'll look at the next type of log, which is a natural log. The big difference here is that natural logs don't have a base of 10, they have a base of e. So again, I'll start with plugging in the 2 for the x. So I have natural log of y equals 3.7. Okay, this time because I have a natural log, my base is an e. So switching into exponential form, my base stays the same. The y and the 3.7 switch, so 3.7 becomes my exponent, and this is equal to y. Again, I've isolated my variable, so I can plug that right into my calculator. 3.7. And I find that y is equal to 40.45. Okay, again, go ahead and pause the video. Try example 5 on your own. All right, we should get 121.51. Again, I've shown my work so you can pause the video and check. As we progress through this unit, we are going to see all different types of graphs. It will help us tremendously if we're familiar with the graphs of the functions we have discussed during our algebra review. So go ahead and take a couple minutes. I want you to graph these 5 equations in your calculator. Once you have everything graphed, then you can unpause the video, check your answers, make sure that you graphed correctly. All right, here we have the answers to the first 4 functions. And then here is that last one. as you're graphing on your calculator, we are used to going to Zoom 9, which always zooms to your stats. Now that we are just zooming to regular functions, it might be helpful to go to Zoom 6, which will always bring you back to your standard 10 by 10 grid on your calculator. If you're looking for nice points as you're trying to graph this equation or any function here, you can always go to your table, which is second graph. It gives you a table of x, y values, which you can use to graph if you want to make your graph nice and precise.